states that the electric flux passing through any closed surface is equal to the charge enclosed by that surface. That means the flux passing through any closed surface is equal to the charge enclosed by that surface. This is the statement of the Gauss law, and we have seen. So psi is equal to, so it is nothing but d psi integral and closed loop integral and dot product of the flux density and the surface vector, that is ds vector. So your ds vector is equal to ds cos theta, so which is normal to the surface. The surface, the closed surface is called the Gaussian surface. The closed surface is called Gaussian surface. So, for example, in this case, if I'm having the flux lines like this, so it is an open surface. Okay, the flux lines are passing like this, and if I have the closed surface or surface like this, which is open surface, which is covering like this, okay, and the flux lines will pass through each areas, that is blue colored ones, and each surface will have its own normal. Okay, in the first line, in the first surface, this is the normal. The black color is the normal, and for the second figure, again the black color is the normal. Okay, normal to the surface. This is the surface, and here the third figure, this is the normal. Okay, the black dotted line is the normal to the surface. The normal to the surface means perpendicular line to the surface. Okay, and the red dotted line is the flux density or the electric field. Direction of flux density is the electric field. Okay, it's the electric field you can talk about. Okay, so what happens here? In this case, in the first case, there is a maximum flux cut by the surface. The second case, half of the flux is cut by the surface. The third case, there is no flux cut by the surface because surface is parallel to the flux lines. Okay. The second figure, it is at an angle 60 degree with respect to the flux lines, and the first case, it is exactly uh, parallel to the means the normal to the surface is parallel to the flux lines. Okay, that is why the angle theta is 0 here in the first case. That is why it is maximum flux. And second case, there is some inclination with respect to the flux lines. So therefore, it is half of the flux lines passing through that small area. And in the third case, it is no flux is being cut by the small area because the angle between the flux density and the perpendicular to the surface is 90 degree. So this is how you can understand how the surface and its normal are represented in a Gaussian surface. Okay, this is a non-uniform closed surface here. So dA represents small areas. dA represents small surface areas, and black dotted line is the normal to the dA. The red dotted line is the electric field. Red dotted line is the electric field. So if ever the electric field and the normal to the surface is parallel, then you can say that maximum flux is being covered by that area. So this is what the inference, and the flux can be positive, the flux can be negative, and the flux can be zero. If the positive charges are more, just crossing the area, then it is called positive flux. If negative charges are crossing the small area, nothing but negative flux, and zero flux. The net flux is zero when the flux entering and leaving the area is the same. Okay, this is how you can understand it. So the flux concept. Okay, now we shall solve one more problem, and we shall get back to the concept. So in a certain take down in a certain region of space, d vector is given. That is, d vector is equal to 2xy into ax cap plus 3yz into ay cap plus 4zx into ez cap. Evaluate evaluate the amount of flux that passes through the portion bounded by y between -1 and 2, z between 0 and 4. They are in x is equal to 3 plane using Gauss law. Okay, so you are required to find the amount of flux passing through the portion bounded by a small surface whose y coordinates ranges from -1 to 2, and z coordinate ranges from 0 to 4, and which is on x is equal to 3 plane, that is x constant plane. So x is equal to 3 plane, that is x is constant. So let me write the coordinates. Okay, so this is the z, y, and x. So x is equal to 3 means which plane I am talking about? Can somebody let me know? X is constant. Yes, it is a YZ plane. I will have to write YZ plane. That means my plane is like this. Okay, so this is my plane. So which is situated at x is equal to 3. This dimension, I'll just write here. This dimension is 3. Okay, and the height, it is 0 to 4. So z is equal to 0 and z is equal to 4. Okay, and y is -1 to 2. So -1 on the negative y-axis and 2 on the positive y-axis. So you are getting a small surface like this. Assume that a plane which is like this. This is the plane. This is the plane which is held like this. Okay. So, and you are required to find the amount of flux crossing this plane. For that, what is that I have to do? I have to choose a small area like this, to choose a small area like this, and also I have to drop a perpendicular. So the perpendicular would be parallel to which axis now? Any idea?
Yeah.
X-axis.
Exactly.
X-axis.
The perpendicular to this surface will be parallel to what? X-axis, because the surface is on ZY plane. So obviously the axis perpendicular to ZY plane is what? X. So this is your AX cap. This is your AX cap, and along this perpendicular you'll be having D vector. Okay, so this is the small ds, and along this you'll be having D vector, that is flux density, and have marked the AX cap, that is a unit vector parallel to the, sorry, perpendicular to the surface of consideration. Okay, so now I need to find the flux, that is total flux. I need to find it. So let me go to the next slide. So I'll just write it here. 5 is equal to closed loop integral d vector into ds vector. Okay, I know d vector. It is given as 2xy into ax cap plus 3yz into ay cap plus 4zx into az cap. Okay, but I need to take the component along the base vector, so which is similar to the unit vector perpendicular to the surface. So I'll write the vector for you. It is 2xy into ax cap plus 3yz into ay cap plus 4zx into az cap. So this is the component of d vector which is perpendicular to the surface. So I need to retain only this part. The rest of things become zero. Okay, or else the dot product of ax cap and uh, ay cap is equal to what? Zero, because the angle between them is 90 degree. So obviously it is nothing but zero. So at the end you will be getting only the terms whose coefficients you have to consider is what? Only of ax cap. So the d cap, or the d vector, is equal to what? 2xy into ax cap. You just have to take. So these two terms becomes zero, negligible. Okay. Next, ds vector, that is a area. So surface area I have to take. So what is the surface area of the um, a portion is given? So how it looks like? It looks like a rectangle. Um, it is whose coordinates are also given. The coordinates which is varying what? Y and z. So the surface area you have to calculate like this. It is nothing but dy into dz, that is length into breadth also, and it is a vector. So obviously you have to drop a perpendicular. So it is nothing but ax cap. Okay, it is nothing but ax cap. So this is d vector and this is ds vector. Take dot product of this one, ds vector. So you will get 2xy into dy into dz. Am I right here? And ax cap into ax cap is what?
1.
1. So because it is a unit vector which are parallel, so the angle between them is 0. So cos 0 is 1. Therefore, you'll get like this. So now d dot ds vector. So psi is equal to d dot ds vector. So closed loop integral, it is nothing but 2xy into dy into dz. So it's a closed loop integral. So here it is double integral. One for z, z is varying from 0 to 4, and one for y, y is varying from -1 to 2, 2xy dy into dz. So on simplification, you'll be getting a 12x. Psi is equal to 12x. X is where it's a constant. Okay. So for example, in my case, x is equal to 3. At x is equal to 3, your psi becomes 12 into 3, it is 36 coulombs. This is the amount of charge, or this is the amount of flux leaving the surface, leaving the surface. So you can imagine now, uh, after the simplification or after solving this problem, what is that you are able to do? You are able to calculate the amount of charge passing through a given surface by applying Gauss law. So this is the application of Gauss law. For example, when you are given a scenario and you are required and you are doing an experiment and you are required to find out the charge involved in it, amount of charge involved in it. So you can apply Gauss law, and then you can find out like this. Okay, the surface can be uniform, or the surface can be non-uniform also. Okay, yes. So this is how we apply Gauss law to calculate the charge contained in a closed surface. Okay, so what you will be given? You will be given the charge density, and you'll be given the type of surface. You will have to find out the surface area, and you will have to make use of that surface area, and you will have to find out the charge or the flux crossing the given surface. Okay, yes. So any doubts up to this point? So if it is, yes, if it is clear, please type 0 on the chat box quickly. Okay, so we shall move on. So let us discuss now the applications of Gauss law. So you have to apply this Gauss law for different scenarios. Okay, so that means you will have to find E and D. Okay, for symmetrical charge distributions. Symmetrical charge distributions, such as point charge, such as line charge, infinite line charge, and infinite sheet of charge. like that. Also, spherical distribution of charge. Okay. So Gauss law is applied for only symmetrical distribution. Yesterday we discussed there is a limitation. There is a limitation. So it's applicable only for symmetrical. So when do you say it is symmetrical? So the system is said to be symmetrical when the charge density is normal to the Gaussian surface everywhere. The charge density is normal to the surface everywhere. Okay? That means the flux density or the charge density, it has to be normal. It has to be normal to the surface of consideration. Okay? So first one, you will have to prove. So this is part of some derivations. I will not go in detail. You can refer it. So first, you will have to verify Gauss law for point charge. Okay, and obtain D and E. Okay, this is about point charge, and repeat it. Gauss law for infinite line charge. Okay, solve for D and E. Next, Gauss law for infinite sheet of charge for D and solve for D and E. Okay, so these are very important proofs. Sheet of charge as well as line charge as well as point charge. So, and also you'll be required to apply the Gauss law or verify Gauss law for spherical shells, spherical shells of charge. For example, this is one shell, this is another shell, and this is another shell like this. So you'll have to apply this Gauss law for spherical shells like this. And lastly, you have to apply or verify Gauss law for uniformly charged sphere. Okay, uniformly charged sphere. So what is that? You will have to uh, observe in each of the um, proofs or each of the derivations what you do. So these derivations are nothing but mathematical jugglery. You just have to concentrate on the inference part and the objective part. So what happens? What happens to the electric field intensity, or what happens to the electric flux density? Variation of the distance, variation of the flux, variation of any other parameter. So like this, you will have to uh, observe. You have to observe, and then you have to draw conclusions. So this is the objective of this part. Okay. So you will have to observe what exactly varying in each of the cases. There, and for that, what is the outcome? That is what you are required to observe, not just simply derive equations and like that. Yet, so firstly, we shall discuss about the point charge. Okay. So first, we shall come back to the point charge, verification of Gauss law for point charge. So we will have to prove that phi is equal to q. That q is the charge of the point charge. Okay. So this is what charge of the point charge. You just have to prove that phi is equal to q in case of this point charge. So let us consider the coordinate system like this, and you're having a point charge at this q, at this origin, point charge q at this origin, and let me assume that there is a spherical surface, which is housing the point charge, which is housing the point charge. 1 second, 2 minutes. Okay, so what happens here? We are interested in finding the amount of charge, the amount of flux leaving this assumed sphere. Okay, so and that amount of flux phi should be equal to what? Q, because that is the amount of charge present inside the sphere. It is assumed like that. So this is z-axis, and this is y-axis, and this is x-axis. So I am interested in taking a small surface like this. Okay. So let the surface be like this. Okay. Like this, it is there. Okay. So what I will do, I will just drop a line like this, and this is my d vector, normal vector, as well as this is symmetrical. I said it is a symmetrical. Therefore, the normal vector and the flux density will be parallel. That means the normal vector and the d vector are parallel to each other, because d vector also is perpendicular to the surface, and the normal vector is also perpendicular to the surface. So this is my region of interest, and this is my AR cap. Okay, so R is what? The distance between this point and this point. Okay, so if you just observe this one, this is a sphere surface I'm interested in finding it. Okay, so what is the expression for flux in terms of Gauss law, we know that. So it is 5 is equal to closed loop integral d vector into ds vector. Okay, so my ds vector, my ds vector is nothing but area of the um, region. It is small region. It is given as r into, okay, r sin theta into d theta into d phi. So this is nothing but a volume, small cube I am finding out, length into breadth into height. So this is a small area, and the direction also is given. Is AR cap. Okay. So finally, ds vector is equal to r square sin theta d theta into d phi into AR cap. So this is my expression for uh, ds cap, ds vector. Okay. So d vector, I already know the d vector due to point charge. It is nothing but q by 4 pi r square, because I know E. So E is what? Q by 4 pi epsilon naught r square. Okay, A r cap. So E is what? E by epsilon naught. So therefore, you'll get like this into A r cap. So this is my D vector. Okay. So now just multiply these two and take an integration over two quantities, one theta and one phi. Okay. So theta is the angle. Theta is the angle between the z component as well as the vector d component, and phi is the azimuthal angle, what we have discussed, spherical coordinate system, azimuthal angle. So it is a varying quantity. R is not varying, theta and phi are varying. So therefore, my limits will be like this. So phi is equal to closed loop integral d vector to ds vector is equal to this phi ranging from azimuthal angle ranging from 0 to 360 degree or 2 pi. I write as 2 pi, and one more theta. It is half angle, so it is 0 to pi. So it is finally, if you multiply d vector and s vector, ds vector, you'll get q by 4 pi into sin theta d theta d phi. If you substitute or if you simplify, you get phi is equal to q. This is the verification of Gauss law for a point charge. Okay. Yes. So it can be said that the proof of Gauss law is from is the outcome of the Coulomb's law. Is the outcome of the Coulomb's law. Okay. So, so I have not gone into the simplification part. So just leave it to you, the integration calculations and all. Okay. So you will have to observe that for any symmetrical charge distribution, the Gauss law is applicable. Okay. Yes. How to perform this one? So first you have to identify the D component, identify the DS component, take the dot product and integrate this dot product over the Gaussian surface. Okay, over the Gaussian surface, and hence you can find charge Q. That's all. Okay, so this is how we do it. Any doubts here? So if you have got any doubts, you can raise it on the chat box. Yes. I'll stop at this point. So we shall continue tomorrow in tomorrow's class. We shall discuss the application of Gauss law or verification of Gauss law for infinite line charge and infinite sheet of charge. Okay, and also the spherical shells. So tomorrow at 8:30, I will be starting the class. Okay, if any change in the timetable is there, I'll just let you know. Okay, so Truth.
Yes, sir. Okay, sir. Thank you.
ಸುಕೃತ್ ಲ್ಯಾಬ್ ಇನ್ನೂ ನಾವು ಪ್ಲಾನ್ ಮಾಡಿಲ್ಲ ಕರೆಕ್ಟ್ ಆಗಿ ಆನ್ಲೈನ್ ಯಾವ ತರ ವಿಡಿಯೋ ಮಾಡ್ತಾ ಇರೋದಾ ಅಥವಾ ಹೆಂಗೆ ಏನಂತ ಗೊತ್ತಿಲ್ಲ, ಇನ್ನೂ ಪ್ಲಾನ್ ಮಾಡಿಲ್ಲ. ಓಕೆ, ಇಫ್ ಇನ್ ಕೇಸ್ ಲ್ಯಾಬ್ ತಗೊಳ್ದೇ ಇದ್ರೆ ನಾವು ಕ್ಲಾಸಸ್ ಎಂಗೇಜ್ ಮಾಡ್ತೀನಿ ನಾನು, ಆಯ್ತಾ? ಆ ಟೈಮಲ್ಲಿ ಕ್ಲಾಸಸ್ ಎಂಗೇಜ್ ಮಾಡ್ತೀನಿ. ಅಕಸ್ಮಾತ್ ಬೇರೆಯವ್ರು ತಗೊಂಡ್ರೆ ನನ್ಗೆ ಹೇಳಿ. ಲ್ಯಾಬ್ ಅವ್ರನ್ನ ಈಗ ಮೆಷಿನ್ ಲ್ಯಾಬು ನಾವಿನ್ನೂ ಪ್ಲಾನ್ ಮಾಡಿಲ್ಲ, ನಾನು ಲೆಕ್ಕಿಸರ್ ಪ್ಲಾನ್ ಮಾಡಿಲ್ಲ. ಬೇರೆ ಲ್ಯಾಬ್ ಏನಾದ್ರು ಪ್ಲಾನ್ ಮಾಡಿದ್ರೆ ಓಕೆ, ದಟ್ಸ್ ಓಕೆ, ನೋ ಪ್ರಾಬ್ಲಮ್. ಬಟ್ ಇಫ್ ಇನ್ ಕೇಸ್ ಫ್ರೀ ಇದ್ರೆ ನೀವು ನನಗೆ ಸ್ವಲ್ಪ ಇನ್ಫಾರ್ಮ್ ಮಾಡಿ, ನಾವು ಸ್ವಲ್ಪ ಪೋರ್ಷನ್ಸ್ ಕವರ್ ಮಾಡೋಣ. ಓಕೆ, ಅದೊಂದು ಮನಸ್ಸಲ್ಲಿ ಇಟ್ಕೊಂಡಿರಿ. ಯಾವಾಗಲೂ ಅಷ್ಟೇ ನಾವು ಒಂಚೂರು ಫೋನ್ ಮಾಡಿ ಇನ್ಫಾರ್ಮೇಶನ್ ತಗೊಂಡು ಆಮೇಲೆ ನೀವು ಇದು ಮಾಡಿ. ಓಕೆ, ಯಾಕೆಂದ್ರೆ ತುಂಬಾನೇ ನಾವು ಸ್ವಲ್ಪ ಹಿಂದೆ ಇದೀವಿ. ಸ್ವಲ್ಪ ನಿಧಾನಕ್ಕೆ ಹೋಗೋಣ. ಇದು ಎಲ್ಲ ಲಾಕ್ಡೌನ್ ಎಲ್ಲ ಮುಗಿಲಿ, ಆಮೇಲೆ ಬೇಕಾದ್ರೆ ಸ್ವಲ್ಪ ರಿವಿಷನ್ ಮಾಡ್ಕೋಣ ಅಲ್ವಾ? ಅರ್ಥ ಆಗ್ತದೆ ಅಲ್ವಾ?
ಅರ್ಥ ಆಗ್ತದೆ.
ಸರಿಯಪ್ಪ, ಇದನ್ನ ಥ್ಯಾಂಕ್ ಯು.
ಸರ್.